In Lesson 3-3, we will discuss properties of logarithms. In video 3.3.5, the learning target is for students to be able to apply change of base formula in order to evaluate logarithms. The change of base formula is for any positive real numbers a and b and x such that a cannot equal 1 and b cannot equal 1. Right? We've already discussed that the base on a logarithm has to be greater than 1 or between 0 and 1. You cannot have a base of 1 because if your base was 1, 1 to any power is going to give you 1. Does not matter how many times you multiply 1 by itself, whether it's 1 squared, 1 cubed, 1 to the 4th, 1 to the 5th, all of these give me 1. That is why they are stating that a cannot equal 1 and b cannot equal 1, because you would end up with a constant function rather than a logarithmic function. Now, if you have log base b of x, then that is equal to log base a of x divided by log base a of b. We will look at the change of base formula as a way to evaluate logarithms in the following examples. In order to evaluate log base 6 of 4, really what you're trying to figure out is 6 to what power equals 4. So what I've done is rewritten the logarithm exponentially. And what we're trying to find, since the word logarithm means exponent, is we're trying to find the exponent on base 6 that would give me an output of 4. Now, sometimes these numbers are not base friendly. Okay, so if we think about this, 6 to the first is x equal to 1. 6 to the first is equal to 6. Well, my output is less than 6, so let's try an exponent less than 1. So let's try 0. Well, 6 to the 0 power is equal to 1 because 6 raised to, or any number raised to the 0 power is equal to 1. So I know that 4 is somewhere in between 1 and 6. Therefore, my exponent has to be somewhere between 0 and 1. I could sit and try every single number. I know x has to be between 0 and 1. So we'll say, just by this estimation that we've done here, x is greater than 0 but less than 1. Well, sometimes it's not very user or time friendly to figure out what the value of x is if it doesn't fit an exact integer, right? So here we go. We know that x is some sort of decimal or fraction, and we don't know exactly what that is. We could use guess and check all day long, and it would take us forever to figure out the exact value of x. So what we're going to do is apply the change of base formula to evaluate this logarithm. Okay, when we want to evaluate log base 6 of 4, we could say 6 to what power equals 4. Now we know that by the change of base formula, we could take the logarithm of both sides of the equation. We could say log of, back that up a second. Log of 6 to the x equals log of 4, right? The reason why I'm taking the log of both sides here in this equation is because a logarithm undoes an exponent, right? The logarithm is the inverse of an exponential function. What I can do here is apply the properties that we learned in lesson 3-2, and I can bring down x times log of 6 equals log of 4. And since I'm multiplying, after applying our power property here of logarithms, I have x equals since I'm multiplying x times log of 6, I can divide both sides by log of 6, and I have my answer. I have log of 4 divided by log of 6 is equal to 0.77 approximately. Now, what we've done here is we've basically changed the base on this logarithm. We started out with a logarithm in base 6, and by rewriting this logarithm exponentially and taking log base 10 on both sides, I could apply the power property and then divide both sides by log of 6 to get 0.77. Now, what you see here, log of 4 over log of 6, the shortcut that we talked about on the last slide there was how did we evaluate a logarithm in base 6 that for a number that is not base 6. We know that our exponent or logarithm is not going to be an integer. So one way we can evaluate this is by saying log of 4, whatever my input is, divided by log of whatever my base is. What I've done is I've converted the logarithms to base 10. This logarithm here is base 10. If you don't see a subscript number, that's automatically a logarithm in base 10, or a common logarithm. So what I've showed you over here with all this work is how you would solve an exponential equation. How you would solve for x if you didn't know what x was. If x wasn't that an integer, if it wasn't that perfect number that you were looking for. So we could use logarithms over here to solve for x. Now, my work over here, solving an exponential equation, is the same thing as they were talking about in the previous slide with the change of base formula. Any logarithm that's in a base other than 10, and you cannot figure out what your exponent is or your logarithm is, you can apply the change of base formula to evaluate. In example 5 part B, we're asked to evaluate log of 1/3, or log base 1/3 of 8 rather, and we know that that's equal to some unknown number x. Well, if I use the change of base formula just says take the logarithm of my input divided by the logarithm of my base, which is 1/3. What I can get here is I have changed the base on our logarithm from 1/3 to now we're in base 10. And our calculator can calculate logarithms in base 10. So I'm going to type in my calculator log of 8 divided by log of 1/3. And I'm going to get approximately negative 1.89. Now, on the previous slide, I showed you how to evaluate, not necessarily kind of memorizing the change of base formula. The change of base formula comes about from solving an exponential equation. So if I rewrite this logarithm exponentially, 1/3 to the x power is equal to 8. That's what we're asking for. A logarithm is an exponent. What is unknown is our exponent. We know our base is 1/3, and we know the outcome is 8. So 1/3 to what power gives me a value of 8? Well, if I take 1/3 to the first, I know that's 1/3. 1/3 squared is 1/9. So my numbers are getting smaller as my exponent increases. I know that 1/3 to the 0 power is 1. 1/3 to the negative 1 is equal to 3. And 1/3 to the negative 2 power is equal to 9. So I know that my exponent is somewhere between -1 and -2 because my output's here. Then we want an output of 8, and 8 is in between 3 and 9. Now, anytime you're solving an exponential equation, what you're trying to do to solve for x, when x is your exponent, you have to use logarithms to solve that equation because a logarithm is an exponent. And a logarithm undoes, or is the inverse of an exponential function. So I would take the log of both sides here, and I'm going to use log base 10, or a common log. And then I can apply the properties of logarithms and move the power down out in front, and I get x times log of 1/3 equals log of 8. And then if I'm going to solve this equation for x, since I'm multiplying x times log of 1/3, I divide both sides by log of 1/3, and I have my answer. Log of 8 divided by log of 1/3. Now, that's my exact answer. I can plug in log of 8 divided by log of 1/3 on my calculator and, of course, get approximately -1.89. So what I wanted to show you, I know that the change of base formula is much quicker, but it's a memorization technique, and I don't necessarily like you memorizing formulas if you don't have to, because you will have to know how to solve exponential equations. And so by showing you work here and taking the logarithm of both sides like I did on the right hand side of this slide, you're really not memorizing a formula, but you're learning a way that you can solve exponential equations and still evaluate a logarithm at the same time. In example 5, you're asked to evaluate log base 1/5 of 25. I want you to go ahead and work this problem out. You have 4 choices, A, B, C, and D, and then I would like you to submit your answer.